All right, so this video is to go over the questions and problems from the first lecture day for chapter 11. In the one section, we didn't have time to go over them. All right, so the first question is asking us to basically identify all the statements that are true if we talk about the magnetic force acting on an electric charge in a uniform magnetic field. So that expression that governs this is the force is QV cross B. And so when we're looking at this, the first two statements are actually, I would mark as true. There might be a specific situation where there's no force, but the point of these two statements is they're really kind of talking about the characteristics of a cross product, where we take two vectors, in this case the velocity and the magnetic field, and we cross them. Those two vectors create a force vector when we cross them that by the nature of the characteristics of a cross product, the force vector is perpendicular to both of those. And so that's what both of those statements are talking about, that the force would be perpendicular to the field for the first statement, and the force is perpendicular to the motion for the second statement. The third statement is not true. If the motion is parallel to the magnetic field, there is no force. If it moves perpendicular to the field, it does feel a force. We would then, if we want to be more accurate, this statement that there's just going to be a force if an electric charge moves through a uniform magnetic field, we wanted to make sure that this wouldn't include a velocity parallel to the magnetic field, which does not create any force. And also, you have to have movement in order for there to be force. So we only have three true statements here. Now, in this problem, and I think the following problem, well, actually probably a couple of these, we're practicing using the right-hand rule to find the direction of the force given different scenarios for velocity and magnetic field. Here, they're talking about electron beams are coming at us, and that's represented by this dot. That's the sort of notation that goes with the idea, if we think of the vector as being an arrow, when we look at it, if it's coming at us, we see a dot or a dot with a circle. And if it's going away from us, if we're over here and viewing it, we would mark it as a cross. So this is a notation we want to get used to for things that are in or out of the page. Out of the page is always a dot, into the page is a cross. So just to get that notation straight. If we do V cross B for this particular problem, we start with our fingers sort of pointing at us in the same direction as the beams or the electrons are coming at us. We want to curl our fingers down. We're using the right hand, of course. Our thumb ends up pointing to the right, so this is the direction of V cross B. This would also be the direction of the force if the charge was positive, but these are electrons. So the force has to be opposite V cross B because of the fact that we have this negative charge because it's a beam of electrons. So the force ends up to be to the left. In this problem, we're doing a similar exercise in terms of trying to practice using the right-hand rule. We want to start with our right hand, and both B and V are somewhat coming out of the screen or the board at us. And so we want to imagine holding our hand along the velocity vector, but then I need to curl it towards the magnetic field vector. I find I have to rotate my hand around in order to be able to have my hand oriented, that I can actually curl towards the B. And that ends up having my thumb pointing down when I do that. So that is V cross B is down, and because Q is positive, force is down as well. In this problem, I have an electron. It's moving in the positive x direction, so here's the velocity vector. And I made that a proton even though I said the word electron, so here's an electron. We're said that it experiences a deflection in the negative y direction, so that's the direction of the force. The magnetic field is going to be perpendicular to the velocity and to the force. And so since the force and the velocity are on the plane of our screen, our magnetic field is either into the page or out of the page. And honestly, we can just check using the right-hand rule for both of these to see which would give a deflection or a force pointing down. We're doing again, F is equal to QV cross B, and keeping in mind that this is an electron. So I lie my hand along the velocity vector, and if I curl my fingers into the board, which is one possibility, I see my thumb pointing up. That's V cross B is up for a magnetic field into the board. And because it's an electron, I know the force is actually in the opposite direction, and so that is actually what I wanted. And so this ends up being the right choice. And that is actually corresponds to the negative z-axis. If we think about our normal coordinate system, x, y, z, positive z is out of the board because x cross y would give us z. We have what we call a right-handed coordinate system. And so you don't get to decide what direction positive z is in. It's actually out of the board. And we found a magnetic field into the board was what we wanted. That's in the negative z direction. Okay, this is another problem that we got to get used to. So when we use the ideas of north, south, east, and west, we're pretty familiar with those directionals. We can imagine that those directions are formed in a plane that is tangent to the Earth wherever you're located. So here's the Earth. But if you think about it, there's another orientation, another dimension, and that is the up and the down. In order to deal with three dimensions. So away from the surface of the Earth, we would call up, and down towards the surface of the Earth, we would call down. In this plane of north, south, east, west, this would be up, and the cross would be down. And so we want to get used to that kind of notation. All right, so we start off with an electron. It's traveling north, so that's the velocity. It says the magnetic field is directed vertically downward, so that would be represented by the x. And then we're trying to figure out what the direction of the force is. So if I put my fingers in the direction of the velocity and I curl my fingers into the page, I get my thumb pointing to the left. But because this is an electron, the direction of the force is in the opposite direction. And so my force is actually to the east. All right, so now we get into a little bit of the usage of the matrix for the right-hand rule. So I'm going to calculate the cross product, I'm going to remind you I did post a video on the landing page for magnetostatics of how we do this if you hadn't seen it previously. My students that had me last semester should be familiar with this. I do a 3 by 3 matrix. The first row is I, j, and k. The next row is the first vector velocity. Our velocity is in the positive z direction at 5 meters per second. That means it does not have an x or y component. It just has the z component. And then the next line is the magnetic field, 3 minus 4, and there's no z component, so I write it like this. And how we do this is we will expand around the top line, and then we're left with a 2 by 2 matrix that's found by eliminating the column and row that coefficient is in. So this 2 by 2 matrix is 0, 5, minus 4, and 0. Then I have minus j hat. We eliminate the row and the column and row that j is in, and I get 0, 5, 3, and 0. And then finally k, we eliminate its row and column. We get 0, 0, 3, minus 4. And then when we find the determinant of these matrices, we multiply these two terms together, and then we subtract these two. So I have I hat, and then I have 0 minus 4 times 5. So that's that term. For j hat, I have a 0 minus a 15. And then for k, I just have 0. So putting this all together, I get 20i plus 15j is my v cross b. My force is equal to the charge, which is minus 1 times this 20i plus 15j. And so it's minus 20i minus 15j is my force vector. And that is D. I wanted to show you another way I could do this because the velocity is just one component. We can actually kind of distribute it to do the cross product. And it's a little device we can use to find the cross product of unit vectors. The way that it works is if I want to take the cross product of like I times I cross j, it's just the next vector I come to, which is k. J cross k is I. So if I want to do a cross product that allows me to go around this circle clockwise, it's always the next unit vector and it's positive. If I need to go around here backwards or counterclockwise to do the desired cross product, it's the next unit vector that I come to, but it's negative. Let's put it into action to see how this works. So the way I could do this is I could do 5 times 3. I don't know why I wrote a k. 5 times 3, and then it's k hat cross I hat. And then I have 5 times minus 4, and then I have a k hat cross a j hat. And so here I have 15, and then I go k cross I actually brings me to j, and I went around clockwise, so that's positive. And then here I have a minus 20, and then I have k cross j. This is where I have to go backwards, counterclockwise, so it's I, but it's negative I. And so for v cross b, I also got 20i plus 15j. And so then the force, because I multiply it by the minus 1, it's minus 20. So I just, all right. Okay, this is practicing the right hand rule. I'm just going to give you the answers because I can't really show you what I'm doing. So if I do V cross B for the first one, it's a positive charge. I end up with a force into the page. The second one, V cross B, gives me a force to the right. This one gives me I cross B. Because if I do I cross B, I get my thumb pointing at me, but because it's a negative, I go into the page. And because the charge isn't moving, the force is 0, because V is 0. And then finally, because V is parallel to B, there's no force either. Okay, and finally we get to this particular problem, which has a lot of numbers, but I'm going to try to do it as neatly as possible. So for A, all these I'm doing F equals QV cross B. My charge is 3.2 times 10 to the minus 19. My velocity for part A is 5 times 10 to the 4th in the I direction. I'm going to cross that with my magnetic field, which is in the K direction. So it's 3.2 times 10 to the minus 19 times 5 times 10 to the 4 times 1.5, and then I have I cross K. If I do my little circle up here, I notice to do I cross K, I have to go around counterclockwise, so that gives me a minus J. And so my answer to this problem, so this one is minus 2.4 times 10 to the minus 14 in the J direction, and that's expressed in newtons. In B, the problem is similar, but I've just changed my velocity to be in the negative Y direction. And so I got all those numbers multiplied together. The cross product I'm doing is J cross K, which I can go around clockwise, and I got I. So the force here is actually going to be the same magnitude, and it's also negative. Oops, sorry. It's in the I direction. And that was in newtons as well. And finally, the last one I'm going to do, it has a 3-dimensional velocity, and so I'm just going to kind of show you the vector, the matrix we create to solve for it. I'm going to try to simplify it, but I'm going to write V cross B. As they did with this, I'm going to take that outside of the matrix and keep just the whole numbers in. I have a 2, minus 3, and 1. And this was all like 10 to the 4th, because it's just, I can multiply everything at the end. And all that I could say times 10 to the 4th. And we already showed you how you do the multiplying for each of the individual components. I would end up with minus 4.5 I minus 3J, and all of that would be multiplied by times 10 to the minus 4. Sorry, that's positive 4. And then to find the force, I just take this and multiply it by Q. And this gives me minus 1.44 times 10 to the minus 14 I minus 9.6 times 10 to the minus 15 J. And that, of course, is expressed in newtons.